Hello, my name is Raychev and I'm the founder of Space Challenges program. Today I'm going to tell you a little bit more about the spacecraft technologies, about the satellites and their subsystems. And of course I'm going to tell you a little bit about the applications that we use the satellites for. In order to reach orbit, the satellite should be moving with roughly 28,000 kilometers per hour or 7.8 kilometers per second. This is enormous speed on the ground. However, if you want to stay in orbit around the planet, you need to reach this speed. In general, the satellites can access different orbits. What we call orbit is actually a state of a constant fall, meaning the satellite moves so fast that it literally misses the Earth while following towards it, hence entering into an orbit. But how we launch satellites? Actually, this is a really tricky and extremely expensive operation. We launch satellites and spacecraft in orbit using so-called rocket launchers. The rocket launchers are extremely expensive systems of transportation of satellites and spacecraft from Earth to orbit. In order to reach space, the satellite should, as we talked, reach at least 28,000 kilometers per hour. Imagine now that you need a system that is capable of accelerating you from the ground from 0 kilometers per hour in just a few minutes to 28,000 kilometers per hour. This system, of course, is so complex and so expensive because also it's not reusable. Usually the rocket launcher systems are not reusable, and this makes them extremely expensive. Imagine you fly from New York to Europe, and once you land in Europe, you dispose of the airplane. This is what is happening currently in the rocket industry. However, many private companies and as well the European Space Program are developing different new solutions. The newest launcher of the European Space Agency is called Ariane 6. The main difference between Ariane 5, which is the currently existing in-use rocket of the European Space Program, Ariane 6 is much more modular, meaning that you can literally stack different types of stages on the rocket depending on the payload, its volume and its mass. This would potentially make Ariane 6 much less expensive to launch, and it will also make it much more easy to integrate on the ground. Two things that might open new opportunities for new players in space to launch ever more advanced spacecraft into orbit. Usually the rockets are multi-staged systems, extremely expensive to maintain and operate. The rocket's only purpose is to launch and propel the spacecraft and put it into the proper orbit. From there on, the spacecraft separates from the rocket and becomes operational. What is interesting to understand is once you are in orbit, there are many things that you have to account for in order for your spacecraft or satellite to be functional. And I'm going to talk to you about the main subsystems of the spacecraft and the main applications that we use satellites for. The spacecraft has two main parts, bus and payload. The spacecraft has many subsystems, and those of course are extremely important if you want to have a functional satellite in orbit. The spacecraft of course comes in different shapes and sizes, and it's very important to understand that every spacecraft is customized based on the requirements of the mission. Meaning that always you build the spacecraft and design it around the application that this satellite would perform in space. Now I'm going to talk to you about the bus itself and the 6 main parts of the bus of a satellite. The bus of a satellite has a structure, it has a thermal protection system, it has a propulsion system, it has an altitude determination and control system, it has a communication system, and of course it has electrical power system. All those systems are vital. Even if one of those does not properly function, your spacecraft will not be able to survive in space. Let's start with the structure. The structure is what holds the spacecraft together, meaning the structure holds all the electronics, the thermal, the controls, the electrical parts, and protects the satellite. This is very important because the structure comes in many different sizes and frames, and usually it's very complex to manufacture. In the current traditional aerospace sector, the materials that are used to manufacture structures for satellites are usually metals such as magnesium, aluminum, titanium, and also lately composite materials and nanotubes. This is very important because once you are in space, the temperature differences are quite severe, and your structure has to not only maintain structural integrity during the launch of the satellite on board the rocket and survive the vibration, survive the shock of the separation of the different stages of the rocket, but also it should survive the temperature differences once in orbit. In order to survive the temperature differences, of course, we have a so-called thermal protection system. Thermal protection system is vital. Why? Once you are in orbit, the temperature fluctuation is really serious, meaning that a spacecraft can easily be exposed to temperatures of minus 100 degrees Celsius to up to 126 degrees Celsius in low Earth orbit. Now imagine your spacecraft. It is in a constant stress test mode. Why? Because on higher temperatures it expands. Once it is exposed to lower temperatures, it shrinks. The thermal protection is vital for the spacecraft, and the reason is very simple. It protects all the electronics and the payload from the harsh environment of space. Why? Because the fluctuation of temperature in low Earth orbit and in space in general is so violent that a normal electronic block could not survive easily if it's not protected on thermal level. There are different isolation materials, there are different techniques of how you heat or cool your system once in flight, because you have to maintain certain temperatures in certain parts of the spacecraft, and this is extremely vital. Of course, the satellite needs a communication, because if the satellite cannot communicate with the ground, obviously it will be a mission failure. The communication of a satellite is extremely difficult to design, and it has to perform very well in the conditions of space. At the same time, satellites use different types of antennas, spot beam antenna, parabolic antennas, and also phased array antennas. Depending on the orbit, depending on the mission characteristics, and depending on the spacecraft size and power capability, the satellite uses one of those different systems of antennas. Communicating with the ground once you're moving with extremely high speeds is very difficult, especially if you are not in a geostationary orbit. The spacecraft flies in low Earth orbit. The satellite flies around the Earth literally 16 times per day. It passes on top of a ground station or an antenna on the ground through which it can communicate and transmit its data for no more than 5-6 minutes on each orbit. This means that the satellite communication system should properly function, should be able to track the antenna on the ground, and should be able to transmit the signal despite the different weather conditions on the ground. In order to ensure the communication with your satellite, excessive testings are performed on the ground before launching. You have to be sure that the antenna spot beam is right, you have to be sure that the signal is right, you have to be sure that the command and control systems connected with your communication block on the spacecraft is right and properly functioning. This implies a lot of rigorous testing. Without communication, again, the mission will be a failure, so the communication is one of the most vital systems on board any satellite. Each spacecraft has also attitude determination and control system. This is a vital system. It's basically the system that orients the spacecraft while flying in orbit, and at the same time it makes correctional maneuvers so that the spacecraft remains oriented for the entire duration of the flight. The determination control system is very complex. It implies the usage of different sensors, such as sun sensor, temperature sensors, sometimes star trackers, accelerometers, gyroscopes, magnetometers once you're in lower orbit especially. Those sensors gather information about your relevant position and orientation at any given moment of time while you're flying in space, and at the same time the spacecraft has a so-called active part of the control system. Once it gathers the information from the sensors, the spacecraft has to react and control its orientation. This is done usually by either momentum wheels or even thrusters, depending on the scale of the satellite. This is the active part. This is what we call the active part of the determination control system. On the electrical side, it is really important that all your electronics can survive the harsh environment in space. In space, of course, the radiation levels are much higher. The temperature differences, as we discussed, are quite extreme. So your electronics on every level have to survive easily in space. This is very challenging because we have to test rigorously on the ground every component that is going to be implemented on board the spacecraft in order to make sure that the electronics can survive for longer periods of time in space. Why? Because if something fails, you cannot send someone to repair your electronic block while flying around the planet Earth. And of course you need solar panels to generate electricity in space. The solar cells are extremely expensive and very fragile once they are assembled on the spacecraft. For space missions usually we use solar cells that are with much higher KPI, but at the same time much harder to produce and much harder to assemble on the solar panel. You have to ensure that all those systems are properly tested. Why? Because only very well tested systems can perform well also in space. Therefore, on the ground, multiple laboratories are constantly testing new technologies, materials, and even the fully assembled spacecraft in order to ensure that no problem would arise potentially while they are in operational mode in space. One example is that in order to test the propulsion systems, you have to rigorously test the performance of the battery, the performance of the electronics, the performance of your communication systems. You have to make sure that during the launch they survive the vibration and the shock testing of the launch vehicle. You have to ensure that once they're in orbit, they survive the harsh environment, the temperature differences and the radiation in space. Validating your technology on the ground guarantees the success of your mission. Last but not least, of course, most of the spacecraft and especially satellites, they have propulsion systems. Propulsion systems are different types, mainly used in low Earth orbit. Most bigger sized spacecraft use technologies such as chemical propulsion thrusters. However, for smaller sized vehicles and satellites, usually we use also electrical propulsion. Electrical propulsion is quite innovative, but at the same time it doesn't give you the same thrust capability as the chemical propulsion. Now, the main reason why we launch satellites in space, of course, is the application. And every application requires you to fit in the satellite concrete payload. The payload is the reason why we launch spacecraft in space. The payload can be camera, sensor, any type of experimental gear that you want to test in space and validate in space. There are many applications, and of course, people in 21st century are completely reliant on satellite infrastructure in space. Why? Imagine your daily lives without communication, without broadcasting. Now imagine your lives without meteorology or without point-to-point communication or without navigation. No modern nation can survive without having navigation system up and running. Therefore, the satellites are absolutely vital for the development of our modern society. Let's talk a little bit about different applications. In communication and broadcasting, the satellites are obviously used for communication and telecommunication. In this sense, the satellites in geostationary orbit are used to retransmit signals for both internet and TV and radio stations all around the planet. Since the distance between the geostationary orbit and the ground is around 36,000 kilometers, the spot beams that this satellite could cover is basically 1/3 of the planet's surface. It's very easy to cover vast areas of the ground using telecommunication satellites. Of course, we use satellites in modern days for science. Earth observation is the major topic, of course, because satellites are used on daily basis to monitor different types of disasters, to monitor the environment and how our planet Earth's nature is changing on daily basis on global level. Only through satellite you could basically understand the profound changes in our nature on global level. The science done and performed in low Earth orbit and in higher orbits is essential for the future human space missions outside of Earth. Why? Because only by rigorous testing in orbit and validating different technologies, afterwards we are able to create more advanced spacecraft technologies based on those initial testing campaigns in low Earth orbit and ensure that the astronauts and cosmonauts could survive in space. When talking about science, other main topic is astronomy and astrophysics. There are vast new discoveries happening every day in astronomy and astrophysics world thanks to flying observatories around the planet Earth. It is very difficult to create observational satellites and extremely expensive, and therefore usually those science missions are designed, engineered and built by space agencies. Of course, satellites are used, and spacecraft in general are used for exploration. One very good example is the extremely successful mission of Rosetta, the first human-built spacecraft who managed to reach a comet and actually return to the Earth absolutely essential data about the composition of this comet, about its behavior. And for the first time, a human-built spacecraft even managed to land on the same comet. This is one of the major contributions of the European Space Agency and the European Space Program in general for the global science community. Satellites and spacecraft are absolutely vital for the human space exploration as well. Why? Because in order to send astronauts to the moon or potentially in the future to Mars, one needs to understand absolutely well and in detail the local planetary environment on Mars, the local conditions on the moon. Therefore, we send satellites and spacecraft to explore these places and to ensure that we understand every detail about their atmosphere, about their composition, about their surface, about the radiation levels, so that we make sure that once an astronaut lands, he or she will survive without a problem and will be able to perform well. The spacecraft that we send all around our solar system return every time vital new information through which we learn more about our near cosmos, the solar system. Of course, the applications that we rely most upon, the public services applications and meteorology. Just imagine if we don't have satellites, how the world would look like without this absolutely detailed information on meteorological situations all around the planet on a literally minute basis. At the same time, all the transportation logistics industries on the planet Earth rely on navigational systems. European Space Agency, in collaboration with European Union, are developing a new generation of navigation service called Galileo. Last but not least, satellites are used, of course, for disaster management and relief efforts. Why? Because imagine an earthquake. In order to assess the damages, in order to monitor the behavior of the Earth mass on the ground, you totally rely on satellites data. For both human-based disasters and natural disasters, satellites are our first line of defense by providing vital data on a global scale. In the area of Earth observation and disaster management systems, European Space Agency, in collaboration with European Union, is the main contributor, designing one of the most advanced Earth observation systems on the planet called Copernicus. So this is a brief overview about satellites and their applications. In principle, we really rely on satellites for our daily lives. Although you don't see them physically, we rely on them for communication, for navigation, for meteorology. We rely on satellites for disaster management, relief efforts. We rely on satellites to understand that planet Earth is a very fragile environment, that we need to protect the natural resources of the planet Earth in order to survive as species. European Space Agency main contributions are both in the navigation, in science and in Earth observation. And we as Europeans have a really big role in expanding further the space frontier by designing ever more advanced systems helping humanity understand better the near cosmos.